Okay, the name of this paper is An Accumulative Model for Quantum Theories. The publication information is here, Electronic Journal of Theoretical Physics, published in August 2015. And the general premise, basic premise of this article is that rather than considering the universe as a process in time, if we think of the universe as an outcome of a process that occurs in a larger space, then we can explain many facts about quantum theory. We can explain in particular the nature of the squared wave function, and quantum paradoxes can all be resolved in terms of this picture. So in this presentation, I'll try to explain to you the nature of this process and show you some of the mathematics that verify that this process does indeed produce the Born probability rule that the square of the wave function gives the probability density. Okay. Now, in the introduction, I draw a parallel between the work in this paper and the work of Boyman-Hiley, who also consider that there's a pre-space which is more fundamental than the visible universe that we see. Now, I should say that I was not aware of Boyman-Hiley's work until after I completed the paper. I just want to point out that this is, in some respects, a parallel line of thought. I also refer in the introduction to our previous paper, which looks at the two-slit experiment in somewhat similar fashion and explains the phenomenon of indeterminacy in terms of an accumulative model. In this paper, we go into more detail and explain the fields that are simply presumed in the earlier paper. Now, before introducing the full model, I'll talk about a preliminary model that introduces the ideas, but maybe in a somewhat more palatable way. So let's consider the following question. Consider the universe as a whole. What determines the probability of the state of the entire universe? So think of the universe as in all of its space-time. And we can consider the possible states of the universe as the set big U, and let U be the state of the universe that we actually see. Right. So from a quantum mechanical point of view, the probability of the universe is derived from its wave function, and the wave function, from the path integral perspective, is obtained in terms of this quantity. Now, I don't actually need this here, this normalizing quantity, because I divide later anyway. But think of this sum as a sum over paths, where each path belongs to the paths associated with the state U, of e to the I times the action associated with the path gamma. Now, I'm being sloppy about factors of h bar, but it doesn't really matter. So this expression is used to get at the probability of any state, possible state of the universe. And the actual expression is down here. We take this psi of u, this sum over paths for u, and then we have to divide by the similar sum. I neglected to say, but you can see here that you take this psi squared divided by the sum over psi squared. That's to normalize in order to make it a probability. So what we're expressing here is that the probability is proportional to this path integral expression up here, this path integral, which is expressed as a sum over paths of e to the I times the action for that path. There's a, you can read Feynman's Nobel lecture, how he came across this realization. It's kind of a interesting, amusing read. All right, so there's some unusual things about this expression for a probability. It's not the kind of expression you usually see in physical models for a probability. The probability is proportional to the square of a complex amplitude. Right? So why is that? A very strange way of obtaining probabilities. Another thing is that you're dividing by all of these other squared amplitudes. And if you think about it, what that means is the probability of any outcome of the universe also depends on the outcomes that are not attained. So this seems like a very strange situation. How can this possibly be? How can the probability of the observed outcome, attained outcome, depend on the probability of other outcomes that are not attained? So we'll see how that can work later on in the paper. All right. Now, the fact that we have a summation, the fact that this psi is obtained as the sum, seems to suggest that there's some kind of process of accumulation. So I'm going to define an accumulated amplitude as a sum of a certain number of terms of this form, okay, where gamma k is a sequence of paths. Now you can think of this as a discrete approximation to a continuous integral. And you can think of this process as the universe, or I like to say the pre-universe, varying through various configurations which are expressible by these paths. And then you're simply summing up this term which results from the universe passing through these paths. Now what could this correspond to? There's an analog. If you think of a harmonic oscillator, which is subject to perturbations. Now, perturbation has both amplitude and phase, so it can also be represented as a complex number. So if you successively perturb a harmonic oscillator, then the harmonic oscillator changes in amplitude and phase, and the accumulated amplitude and phase is expressed by a sum, where the sum is the sum of terms coming from each perturbation. Okay, so I guess what I'm trying to get across is that analogously we can consider the universe, or pre-universe as it were, has an oscillation associated with it, and that oscillation grows in amplitude, and we'll see that the way the actual universe is obtained is when this pre-universe attains a threshold in the amplitude of its oscillation, and that determines the actual state of the universe. Okay. Now, this process of accumulation can't depend on time because time configurations are part of the final outcome, because I'm talking about the outcome of the entire universe. So this process must occur not in space-time, but in another dimension. So we call this the A dimension. So that's the basic idea. Process in the A dimension, a process of accumulation in which the pre-universe has an oscillatory amplitude, and this amplitude grows to a certain size. Once the amplitude reaches a certain threshold, then we obtain the visible universe. Now, let me show a picture which I hope may be helpful. This is supposed to show the trajectory of the pre-universe. Now, this large box is the space of all possible paths, those that I've indicated by gamma. So all possible gammas are included in this box. Now, we also know that for each observable state of the universe, there are several gammas. So I'm dividing this space of paths into observable states of the universe. And what I'm saying is that there's a process during which the configuration of the pre-universe varies, and we can represent this variation of the configuration of the pre-universe as a wandering through this path space. As the pre-universe wanders through this path space, the oscillatory amplitude increases until it reaches a threshold. Now, at the point where it reaches the threshold, it will be in one of these states, and this state where it's located at the time the threshold is attained, that's the observable state of the universe. So that's the basic idea of the process. There are more details later on that a little more complicated, but this is the basic idea. I should also mention that I'm not thinking of the pre-universe actually wandering in a larger space. This is simply a mathematical representation of the fact that the configuration of the pre-universe changes. So this large space is the configuration space of the pre-universe. Now, how do we translate this picture mathematically? Let's go down here. So there's a mathematical specification of a random process. And let me jump back to the picture here. I have a picture up top here, which I hope can be helpful. I say that this process of wandering of the pre-universe does not take place in the time dimension. So this path, this trajectory is not parameterized by time, but by the A, what I call the A dimension. And I'm going to divide the A dimension into blocks of size nm. And in each block of size nm, the pre-universe is located in one of these possible configurations of the space-time universe. I'm further going to divide these blocks into smaller blocks, and associated with each one of these smaller blocks is a random variable that I'll explain later. At this point, it's not explained, but it's just a mathematical device to make things work out. And then here are the sums over the individual paths. Okay, so I'm summing over individual paths as I move along. So that's my process of integration. And then every interval, I multiply that by a certain random variable. And then after every interval of size nm, I move from one box to another. Okay, so this is a very simplified picture. You notice that what this is saying is that I'm assuming that the process spends equal intervals in each state, each possible state of the universe. So it would spend equal interval here and here and here and so on. So you can see from this picture that doesn't really appear to be very realistic. I'll relax that assumption later. And while it's within one of these boxes, there are further subintervals where something else is going on, okay? And which I'll leave physically unspecified, but mathematically will represent as multiplication by random variables. Okay, so that's basically the idea behind these assumptions here, ABC. Now, the proposition is that if I do have this model, and I have this action defined by the usual action used in quantum mechanics, that the probability of the state where the pre-universe is located when the accumulated amplitude reaches a threshold, that if you assume that this sequence is mixing and there's some other technical assumptions, that the probability of the state that is attained is exactly equal to the quantum probability. You get the square of the magnitude of the complex wave function. Okay, and there is a mathematical proof based on the proof given in our earlier paper. The idea is that you can represent this process as a Brownian motion in a limit. And well, actually, you represent the growth of the accumulated amplitude as a Brownian motion in complex space, and then you find that the probability is proportional to the squared amplitude, and that gives it to us. Now, at this point, we performed some simple simulations to verify that this model does work. In these simulations, we didn't actually do a path-by-path accumulation. We did accumulation block by block, where we used these blocks of size, the blocks of size m. I'm sorry, should go to this here. We accumulated by blocks of size m, and we showed that, in fact, the error, the difference between our model's predicted probabilities and actual quantum probabilities is decreased as you increase the threshold. These are two different configurations for the wave function. In both of these cases, we took 11 states with different wave function amplitudes. In this case, the wave function amplitudes were equally spaced, and in this case, the square of the wave function amplitudes were equally spaced. So the shapes look a little bit different, but notice this common feature that for large amplitudes, our model predicts lower probabilities than the accepted quantum theory. So you see these numbers are negative. And then for smaller mid-range amplitudes, we expect a probability that's slightly bigger than that predicted by quantum theory. And I can represent this in the following way. If we just simply schematically draw a wave function, just let me roughly sketch one. There's a wave function, not particularly one. But there's a wave function. So this is, I can have this be the x direction, and this is going to be psi squared. What our model predicts is that the peaks are slightly flattened, and the intermediate regions are slightly amplified. Okay, so something like this. This is not a very good picture, but I hope you can get the idea that the peaks are flattened and lower probabilities are amplified. That's what we predict, and we predict the deviation is going to have roughly this kind of shape. Okay, so that's an encouraging partial result. And you notice that these numbers are quite small, and we run larger simulations later on, and we show that in fact that we get better convergence. The convergence is not just temporary, but it actually does become closer and closer to the quantum predictions as we vary the parameters, make them larger. Okay, so our simple model gives a concept, but there are some artificial features that seem imposed. For instance, why should the state of the universe in this process remain constant for constant size intervals? That seems unnatural. Why should the states switch suddenly from one to another? And that's not continuous. It just does not seem physically something that would occur. We also have introduced these random variables which we haven't explained. Okay. So as to the first point, we consider that this process of wandering within configuration space is a Markov process, and Markov processes usually have residence times that are roughly geometrical, geometrical being the discrete analog of exponential. So we're going to replace these constant intervals with with exponential distribution. Okay. So, or actually geometrical distribution, because we're doing this all in a discrete model, discrete analog. All right. Now, so we'll introduce that into our new formulation. Now we need to tackle the significance of these etas. And I'm going to deal with these by saying, so far we've lied to you. I've said that I'm talking about the state of the entire universe, but actually, practically, we never measure the state of the entire universe. We only measure the state of a subsystem. So let's consider the case of a subsystem of the universe, not the entire universe. In that case, we have a situation more like the following. Here on the plane, I've listed states of the observable system, but for each state of the observable system, there are several states of the external system that's not observed. And we suppose that the wandering of the pre-universe through configuration space varies through both observable states and states of the external system. And we're going to split up our wave function into a product wave function, the wave function for the observable system and the wave function for the non-observable system. And we'll see that this wave function for the non-observable system is what's responsible for these factors eta, these random variables. And because the wave function is multiplicative, it's going to be a multiplicative factor. Okay, so I think this really gives the full picture of the process. Again, the pre-universe goes along this trajectory, all the while it's accumulating an oscillatory amplitude until it reaches a certain amplitude, and at that point, whatever observable state we're in is the observation that we make for this current universe. Okay, so here you see some of the mathematical properties. We're factoring the wave function into the wave function for the observable state and for the non-observable state. We write the accumulated amplitude in this way. So we split up paths into the path for the observable part and the path for the non-observable part. And then here's just some technical stuff to model the picture that I've shown you in the PowerPoint slide. So you get a slightly more complicated sum, but you end up getting the same result. You end up finding that the probabilities of ending up in any visible, observable state is also proportional to the squared amplitude of the complex wave function. Okay, here we did a more sophisticated, larger simulations where our wave function was this sign, the squared wave function is this other sign, and states had different amplitudes, and we plotted the probability observed in our model versus the squared amplitude, and you can see it follows very closely. You can see we have the same pattern of deviation. This is for different values of the threshold. The larger the threshold, the closer the approximation. But we still have this pattern where smaller probability densities are larger in our model than the quantum prediction, and large probability densities are lower in our model than the quantum prediction. So we vary the threshold here. Here we vary the accumulation length, and in both cases we can see that as you increase the parameter size, you get better and better approximation to quantum probabilities. But we would expect at some level there would be some deviation from the theoretical accepted quantum probabilities, and the deviations would have this kind of shape. So that's the basis for the experimental test, that in fact the quantum wave function densities will not be quite exactly what are predicted by quantum theory, but there will be deviations, and the deviations will be basically flattening out the wave function. Now, I claim that this model solves all quantum paradoxes. It seems like a rather vast claim, but my claim is based on the fact that quantum mechanics is based on path integral formulation, the path integral mathematics. If you can explain the path integral mathematics, you can explain quantum mechanics. And this process, although it may be unfamiliar to people, it really is not such an unusual and esoteric process. In fact, you see similar processes in wireless communications. If you have a cell phone that's acquiring a signal, the cell phone wanders through space and it acquires a signal, it accumulates. It's looking for a particular signature and it accumulates signal according to that signature. Once it reaches a certain threshold, it registers a detection. So actually that was my original inspiration for coming up with this model. And there is a practical exemplification of the model that I think helps to clarify what's going on in the model. And again, here that you have to think of the analogies that in this case, I'm not talking about the universe wandering through a physical space. This is just configuration space, but the process of accumulation is analogous and the process of detection is analogous. Now, in this picture, I want to show that, for instance, the collapse of the wave packet is not an issue anymore. Why? Because the quantum probabilities are characteristic of each of these observable states. Once I reach the observable state, the entire state is determined past, present, and future. So there's not a collapse that happens in time. There's simply a detection that takes place that determines past, present, and future. So there's no collapse. We also have no problem with quantum non-locality in EPR because you can see that the entire state, past, present, and future, is determined at the same time. So you could say that what we call causality is really correlation, that there are correlations between past and future, and we identify that as causation. But if you look at the origin, that really these are coming from the fact that the past and future configuration determines that the state has a large amplitude, so it's more likely for the pre-universe to log a detection and become our observed universe in that configuration. We also speculate some other, or notice some other things, is that, as I mentioned, the original analogy that suggested this model comes from technology. And in the past, in the history of physics, many analogies have served to cause breakthroughs, conceptual breakthroughs in physics. For instance, Einstein, space-time, thinking of curvature. The analogy with curved space made him think of curved space-time. Planetary model of the atom, Maxwell, relating electromagnetism to stress and strains in a fluid, and so on. So these are all natural analogies, and I'm saying that now we have technology, we may find that some analogies from technology cause us to have deeper understandings of what's going on in physics. Okay. Some other possible future work, here's the simulation code. You can try out the simulations for yourself, but I leave that to you. I think that's enough detail for now. Thanks for listening.